In problem number 2, we're asked to talk about population of bacteria. T is measured in days. They give us a differential equation to represent the rate of change of the bacteria population. And in part A, we're asked to solve this differential equation, or at least find the general solution, without using a calculator. So for part A, let's go like this. We'll copy the differential equation, dp dt equals 3,000 over 1 plus 0.25 times t. So in order to solve a differential equation, we have to identify what was differentiated to give us this equation. See, this is the derivative of p with respect to t, so we need to get all the p's on one side and everything else on the other. So dp dt equals 3,000 over 1 plus 0.25 times t times dt. All right, so now let's integrate each side. The integral of dp is going to be p plus a constant. The integral of 3,000 over 1 plus 0.25 t. This one's going to require some substitution. So let's let u equal 1 plus 0.25 t. Then du dt is 0.25. If we solve for dt, we get du over 0.25 equals dt. Now here's a move you don't have to make, but divided by 0.25, that's the same as multiplying by 4. So you could say 4 du equals dt. So we have a u, we have a dt. Let's get to work. It's going to be like integrating 3,000 over u times 4 du. Oh boy, let me move some of this stuff over so it's not too crowded. There we go. Okay. Well, now the next move would be to take this constant 3,000 out in front of the integral, and also take out the 4. So we take out 3,000 and then a 4. That's 4 times 3,000. That's going to leave us with 12,000 out in front of the integral, times the integral of 1 over u du. Now this should look recognizable. So it's going to be 12,000 times the natural log of the absolute value of u plus a constant. Well, technically it's like this. Oops, constant 2. So now we'll differentiate, we'll distribute, and we're going to get 12,000. And let's also substitute times the natural log of the absolute value of 1 plus 0.25 times t, plus 12,000 times the constant, which is a different constant. Okay. And it looks like I failed to write in the first part of the equation. Oop, I don't know why that's so thick. Let's go back to here. Okay, let's do this. Remember on the left side we had p plus a constant 1 equals. So this is so now to get p by itself, we're going to subtract constant 1. We'll say p equals 12,000 times natural log of the absolute value of 1 plus 0.25 t plus constant 4, or just a constant. This is the general solution to our differential equation. This is the answer to part A. Now in part B, we're supposed to find the population when time equals 3 days if the initial population is 1,000. So let's keep this in mind. And we're going to find the population when time equals 3. So let's do some work here for part B. Let's see. Here's our general solution. P is 12,000 times the natural log, the absolute value of 1 plus 0.25 t, plus a constant. And let's see what can happen. We're allowed to use a calculator. I don't think we need to use one yet. They told us that p is 1,000 when t is 0. So we replace p with 1,000 and replace t with 0. And let's see what we get. Let's see. 0.25 times 0 is 0 plus 1. 1. Natural log of 1 is 0. So we get 1,000 equals c. So that means we have our particular solution is p equals 12,000 times the natural log, the absolute value of 1 plus 0.25 t, plus 1,000. Here's our particular solution. Now they want us to evaluate this when t equals 3. They said, what's the population after 3 days? So say p is 12,000 times the natural log of the absolute value of 1 plus 0.25 times 3 plus 1,000. Now we want to use our calculator. So we type this in our calculator and you get that P is approximately 7,715 bacteria. So it's talking about a population of bacteria. We're not going to include any decimals. We're going to round to the nearest integer. So now let's answer the question. At time equals 3 days, the population will be about 7,715 bacteria. And that's it for problem number 2. Hopefully this was helpful. Thanks for watching the video. Have a great day.